physics of sound. In this video, oscillations and waves. Just understanding the words.
Swing the end of a rope and you will see the frequency traveling.
Oh no, frequency traveling?
I gave the pendulum a push and allowed it to resonate freely.
Resonate freely? Ha!
A guitar string is a simple oscillator with many vibration phases.
You say that's simple?
In wind instruments, the sound is a traveling wave going from the mouth to the horn.
That's a standing wave.
There is no resonance if the driving force is out of phase.
You probably mean out of frequency. Oh. Stop the sound of ignorance. All it takes is learning the meaning of a few words. Once their meaning is understood, the sound of ignorance will be gone for good. Let's start with the first term. Oscillations. Oscillation is the motion around an equilibrium position. These are examples of oscillations. These are not. According to why are oscillations happening, these can be either free running or forced. One way to produce oscillations is by disturbing the equilibrium with some initial force and then allow the system to run free. It doesn't take a genius to figure that this is the free running oscillations, right? However, in the real world, those oscillations will not run forever. Friction will drain away the initially provided energy and oscillations will eventually stop. It's a video of one real pendulum made of a very real orange. It finally stops. But even in the real world, oscillations will not die off if there's a driving force pushing periodically. These are forced oscillations. There are words to know about the free running oscillations: damped, underdamped, and overdamped. Free running oscillations are also called damped oscillations. The reason for calling them damped is obvious. In the real world, there's no such thing as an undamped free running oscillation. Damping comes in two flavors. The underdamped, which is the one that actually oscillates, and the overdamped, well, that doesn't oscillate at all. And there's a third flavor, the in-between one, which happens to be the fastest way for returning to equilibrium, and it's called the critically damped. And there are the forced oscillations, which involve a quite familiar word: resonance. Forced oscillations. When a periodic force acts on an oscillator, it moves to that rhythm. How much it moves? That will depend on the pace at which the periodic force is applied. In other words, on its frequency. Mass spring systems like this one will show preference for one frequency, one at which they respond with the greatest oscillations. This effect is called resonance. Past this frequency, it will be back to small oscillations. Some stories have made the resonance effect famous. It is said that Caruso, the famous Italian tenor, had such a powerful and well-tuned voice that it could break a wine cup. Some resonance effects have been dramatic. When a strong airflow encounters an obstacle held in place by some elastic means, turbulence makes it oscillate. The effect is known as vortex shedding, and it's how sound is made in some musical instruments. Here's a video showing the effect in a small scale. And here's a disastrous greater one. According to how oscillations oscillate, they can be either simple or complex. Simple oscillators do simple oscillations. These are simple oscillators doing simple oscillations. These are not. These are complex oscillators, for they can oscillate in more than one way. The ways in which a complex oscillator can oscillate are called modes. This spring mesh system may oscillate in this mode. It may also oscillate in this other one. And it may oscillate in both modes at the same time. A string has many modes of oscillation, infinite in theory. Membranes have also many modes, infinite in number as well. Here's the one with the lowest frequency. And this one is perfectly possible too, as well as this other one with a higher frequency. And here's one with even higher frequency. And as every system, all the modes may act at the same time. Complex oscillators not only may free run in more than one mode. When subject to forced oscillations, they may show as many different resonances as they have oscillating modes. Let's watch some resonance modes in a string. We now pick up the pace to find the first resonance. There you are. There's a second one. And a third. Energy loss to air friction makes it difficult to see higher modes. Complex oscillators may be studied in terms of waves, traveling waves, and standing waves. An image tells more than 1,000 words. These are standing waves, and these are traveling waves. Not much remains to be said. Actually, standing waves result from two waves traveling in opposite directions. There are oscillations in which what oscillates is invisible. Air molecules. Yet very much apparent to the ear, for these are sound waves. Air oscillates much in the same way as in a slinky. These are, wait a minute. No, these are transversal waves. These are longitudinal waves. Sound is a longitudinal traveling wave. If the air is confined within a finite-sized tube, the sound wave will no longer be traveling. It is now a standing wave, just like the oscillation strings. Forced oscillation, its modes, and resonance effects are shown in this experiment. The highlighted words are parameters that apply to oscillations. They don't travel, they don't move, and they don't oscillate in space. Are we clear? Oscillations need some parameters, so they can be described. Two of them are amplitude and period. When the period is less than 1 second, it becomes more convenient to express the feature as the number of cycles in 1 second. It is then called frequency and measures in hertz, or the numbers of cycles in 1 second. The unit abbreviates as Hz and honors Heinrich Hertz, a German physicist that was the first to prove the existence of electromagnetic waves. Frequency is also a property of oscillators, but then it must follow a first name. Oscillators with no damping will oscillate at their natural frequency. But since no such thing exists, the free-running frequency at which they will oscillate will always be smaller than the natural. Resonance is always associated with a curve like the one below. It even has a name. It's called the Lorentzian, for honoring Hendrik Lorentz, a Dutch physicist in the late 19th century. The set curve plots the amplitude of the oscillations in response to a sinusoidal driving force versus the frequency of this force. Resonance This amplitude is expressed relative to the one happening at zero frequency. The frequency is expressed relative to the natural frequency. Oscillators with little damping resonate when driven very close to the natural frequency, but smaller. With no damping, resonance would occur at the oscillator's natural frequency. As the damping increases, the resonance effect will become softer and will show at lower and lower resonance frequencies. We're almost there. This is the last word to know the meaning of. Phase. Once understood, the sound of ignorance will be kissed goodbye. Amplitude and frequency applies to one oscillation, while the concept of phase involves two. Phase describes how far ahead or back behind is one oscillation from another. Phase could be expressed in units of time, but that would not be telling how significant it is, unless, of course, it can be compared with a period. Phase is conveniently expressed in fractions of a cycle, so it uses units of angle. That is either degrees from 0 to 360 or 2 pi radians. This video illustrates the use of the phase concept to describe how the driving force and the oscillation displacement relate in its timing. For lower frequencies, below resonance, the movement and the force are totally in phase. When it gets to the resonance, then they are 90 degrees out of phase. Past the resonance, they are totally out of phase, 180 degrees out of phase. Here are a few statements that are almost right, yet they belong to the sound of ignorance. Can you tell what's wrong with them?
This pendulum has a frequency of 1 Hz.
The frequency of this sound will travel far.
Since sound consists of traveling longitudinal waves, so are those on the guitar string generating it.
The modes in a membrane oscillate at different frequencies.
Those two frequencies are always 90 degrees out of phase.
You may look up the answers after the end of the video. This has been the first video of the series on the physics of sound, the purpose of which had been to clarify the meaning of some words that people, unfamiliar with the subject, tend to use improperly. Once you know the meaning of the words, you're halfway to becoming an expert. If you're interested in the subject, subscribe to the channel.
This pendulum has a frequency of 1 Hz.
Oscillations have frequencies. A pendulum is not an oscillation, but an oscillator. However, an oscillator does have a natural frequency, a free-running frequency, and a resonance frequency. For example, this pendulum has a natural frequency of 1 Hz. That will be correct.
The frequency of this sound will travel far.
Frequency does not travel. However, sound, which is a traveling wave, does. A way to say it while avoiding the sound of ignorance would be, a sound of that frequency will travel far.
Since sound consists of traveling longitudinal waves, so are those on the guitar string generating it.
As true as it may sound, it's still false. The standing waves on a guitar string are transversal, yet they generate longitudinal traveling waves. We call that sound.
The modes in a membrane oscillate at different frequencies.
Membranes oscillate, modes do not. Also, a membrane is an oscillator with infinite oscillation modes, and each mode has its own natural, free-running, and resonant frequencies. So, one correct way of saying this would be membranes oscillate in modes of different natural frequencies.
Those two frequencies are always 90 degrees out of phase.
Oscillations may be out of phase, but not frequencies. Besides, only oscillations with the same frequency can be out of phase by a constant angle. Oscillations with different frequencies are changing their relative phases all the time.